We're on number 7. 7 is a piecewise function, so we're going to check it out. We've got z of x. That's how I write my z's. I put a little bar through them. If you don't like that, too bad. Z of x is equal to 2x plus 5 or negative x plus 8. It's just two functions put together, and it equals 2x plus 5 when x is less than 1, and it equals negative x plus 8 when x is greater than 1. Okay, now, the first thing we need to do, just like we did with these other ones here, we can check and make sure z of x is continuous everywhere. When it's a piecewise function, we saw this with the absolute value thing, you check each individual function or piece. 2x plus 5 is always continuous. That's no problem. Negative x plus 8, always continuous. Great. Now the only problem is where it splits. Okay, you have to make sure that when 2x plus 5 ends, it ends right where negative x plus 8 begins. You want to make sure 2x plus 5 is coming up like this, and negative x plus 8 takes over at the same point and just starts doing whatever he's doing. Otherwise, you're going to have something like this. It's going to come up and then start down here. That's not continuous. You got to make sure the y values are the same where they meet. So you do that. Really, just a real quick check is you plug 1 in to both of them because that's where they meet. When you plug in 1 here, you get 7. You plug 1 in here, you get 7. Okay. Now, what you're really doing there when you plug in that 1 is you're really doing the limit as x approaches 1 from below of z of x is equal to 7, which is equal to the limit as x approaches 1 from above of z of x. Okay, so the limit equals, the left-hand limit and the right-hand limit equal each other, so the limit equals 7, and the limit, which just equals 7, because that's what both sides equal, is equal to z of 1, because when you plug 1 in, you got to plug it into this one, because that's where x equals 1, and you get 7. So, and those were our rules for continuity. We had to show three things when we do continuity. Number 1 was that the function's defined, which it is, it equals 7 at 1. Number 2 is that the limit exists, which you show by taking the left-hand limit and the right-hand limit and showing they're the same number, which we did. And number 3 is that the limit equals what the function equals at that point. So the limit as it goes to 1 equals what it equals at 1. So that shows that it's continuous, and it didn't ask you to show that, but that's how you would show that. Now it's continuous, so now we got to wonder: is the derivative the same from the left and right? So we're going to derive it, and that's going to give us 2 and negative 1 when x is less than 1 and x is greater than 1. And you cannot put an equal bar here until you check and make sure they're the same number. And right away you can see they're not the same number. On the left-hand side it's 2, on the right-hand side it's negative 1. So essentially what's happening is the limit as x goes to 1 from below of z prime is not equaling the limit as x goes to 1 from above z prime. So we got a case where the function's continuous. Hi, baby.
Hi.
Where the function is continuous and the derivative is not continuous. The derivatives are not the same from both sides. My wife is here, everybody. So what that means is there's a corner. If the function's continuous but the slopes are not the same on both sides, there's a corner, and you're going to write that. Z of x is differentiable on all reals except for 1 because there's a corner at x equals 1. And if you want to prove it or show it, you would just do those left-hand limit, right-hand limit. Very easy. Number 8, very, very similar. First thing we do, we got this function here, is we check and make sure that each piece meets the other. So, you check each piece out individually first. The first part is a quadratic. He's continuous everywhere. The second part is a linear function. He's continuous everywhere. And the third part, 1 over x, is continuous everywhere but 0, and since he's only defined when x is greater than 3, we don't have to worry about 0. So all 3 individual pieces are continuous on their intervals. Now we got to check where the breaks are. At x equals 0, the top function's headed towards 2, because when you plug in 0 you get 2. The middle function's headed towards 2, so these top function and middle function are going to meet each other. Okay, whatever this quadratic's doing, I don't know, coming down like this, it's going to stop and that line is going to pick up. Then at 3, so this is going to keep on going, so this is at 0, so x equals 0 right there. And then at 3, 1, 2, 3, this line's going to keep going, keep going, keep going, and then jump to this 1 over x. Well, at 3, this thing equals, what, 11 way up here, and this equals 1/3. That's going to be way down here somewhere. Okay? It's not continuous at 3. So, not continuous at x equals 3. So it can't be differentiable there anyway. Now we're going to check out the derivative by deriving the pieces. And that's going to let us know if it's differentiable. So, q prime of x is 2x plus 3. And what's the other one? 3 and negative 1 over x squared. X is less than 0, 0, x less than 3, and 3 is less than x. We know it's not differentiable at 3 because it's not continuous there, so we're not going to put an equal sign. It's continuous at 0, so it could be differentiable there, so we need to check it out. At 0, 2x plus 3 equals 3. At 0, 3 equals 3. So we can't put an equal sign there, because the derivative is the same from both sides. And again, if you want to say that, you would just write the limit as x goes to 0 of q prime of x from the left is equal to 3, which is equal to the limit as x goes to 0 from the right, q prime of x plus. Because that happens, and because it was continuous, the derivative exists at 3. So the question asks where it's differentiable, so we're going to say q of x is differentiable at, or on, let's write on, it's probably better, on all real numbers except for 3, since q of x, and it's not differentiable there because it wasn't continuous, is not continuous at x equals 3. There you go. The other problem point could have been 0, but we checked 0 and it all worked out. Okay. These other ones are very similar. Ooh, 10. I'm going to skip over 9. 9, you got to break this thing apart into its piecewise functions and just show that the left-hand derivative at 5 is not the same thing as the right-hand derivative at 5. Okay. For this one here, though, we got to make sure that this thing's continuous. So basically what has to happen is when you plug in 1, maybe I'll write this out a little bit better. F of x is this big. I'm not going to write this out. F of x is this. We want the top piece at 1, so when you plug in 1 for x, you get a times 1 squared plus 7/6c. That piece has to meet the middle piece.
Right.
Yeah, baby.
How long are you going to be?
Just b minus 4. A minute or two.
Oh, okay.
Okay.
Because you want to watch TV.
Go watch TV. It's fine. We need this to happen. This is when x equals 1. We also need the middle piece, which is bx minus 4, to equal the bottom piece, bx squared plus cx, when x is 2. Again, individually, the top part is going to be continuous because it's a parabola. The middle part is going to be continuous because it's a line, and the bottom part is going to be continuous because it's a parabola. The only problem is going to be where they meet. They have to meet each other at the points where they end and begin. So this has to meet this one at 1, so we plugged in 1 and got this equation. And the middle one, bx minus 4, must equal bx squared plus cx at 2. And when you plug in 2, you get 2b minus 4 has to equal 4b plus 2c. Now the problem with this is showing that it's continuous. If these all these pieces meet, then they are continuous, and that's golden. That's great. The problem is we have 3 variables, a, c, b, and b and c down here, and only 2 equations. So we can't solve that. But we also know that the derivatives have to meet each other at those points. B prime of x, or f prime of x, is going to be 2ax, okay, plus 0, because c is some number. C is a constant, a is some constant, so that's the derivative. This is going to be b, and when you derive this bottom part, you're going to get 2bx plus c. And this happens at less than 1, between 1 and 2, and greater than 2. Now we need the derivatives pieces to meet each other so that we know that the slopes are the same from the left and the right. So not only do we have these equations right here, we're also going to have, I'll write it in green, that when x is 1, 2a, that's what you get, has to equal b. There's nowhere to plug in x here, that's fine. It's just b. And at 2, b has to equal 4b plus c. Now we've got a bunch of information here. We've got these two equations, we've got the other equations here. Now we can solve some stuff. So let's do this. First off, 2a is equal to b. Alright, that's fine. What that means is, let's erase this. This is just a derivative. We got our equations. We don't need it anymore. That 2b minus 4 is really going to be 2 times 2a minus 4. And that's going to equal 4 times b again is 2a plus 2c. I'm just doing a little bit of substitution here. So we get 4a minus 4 is equal to 8a plus 2c, which is going to simplify down into negative 4a is equal to something here. Negative 4a is equal to, what, 4 plus 2c. And I'm just going to solve for a, because this is just, again, a system of equations. We got to simplify it down. Okay, so a is going to be, divide by negative 4, negative 1 minus 1 half c. We're going to use this in combination with this and plug both of them into this first equation, and the only variable that's going to be left is c. Here's how we're going to do it. We can erase this. A is negative 1 minus 1 half c plus 7 6c has to equal b, but b is just 2a. And a is just this thing. So it equals 2 times negative 1 minus 1 half c minus 4. Now we have an equation with just c. So let's simplify it down. First off, well, negative 1 half plus 7 sixths. What's this? 6 twelfths, 14 twelfths, 8 twelfths. Plus 8 twelfths c. This is going to be negative 2 minus c minus 4. And simplifying, negative 2, negative 4 is negative 6, plus 6, we get 5 is equal to minus 8 twelfths, this is 12 twelfths, negative 20 twelfths c, which means you're going to get 12 times 5 is 60 over negative 20, c is negative 3. And if c is negative 3, a is going to be, is this right? C is negative 3. I think that's right. A is going to be, well, C is negative 3. This is what? 3 halves. Negative 1 plus 3 halves is 1 half. And if B is 2A, B is 1. There we go. That's what our equations led us down to. You can plug them all back in to make sure your equations work, but I'm pretty sure these are the right answers. I'm fairly amazing. Actually, I checked this before I did this, so this is one of the rare times that I'm fairly sure that I'm right. All right, that's it. Congratulations. Happy Halloween, whatever you're doing. I don't know. Take it easy.